currently a member of the technical staff here at Cohere, where he is part of the RL research team. Arash was actually previously part of our C4AI Scholars Program, where he worked on RLHF and alignment. He also worked on post-training quantization at scale and mixture of experts. And before that, he was a researcher at Vector Institute working on model-based RL and LLMs. I've had the pleasure of working closely with Arash and meeting Arash in person since he was on the C4AI team. So I'm really excited that he is here presenting. So I'll pass it over to you, Arash, and I think we are good and we can see your screen.
Okay, awesome. Yeah, thanks, Britannia, for the intro. So yeah, happy to be here. This is basically the second full-fledged scholar project that I had. The first one, like Britannia said, was on integer quantization, but now this is about RLHF. So yeah, and the title of the talk, I mean, you probably know, is because of this paper, basically revisiting reinforced style optimization in RLHF. As I'm sure all of you know, RLHF and preference training is a super hot area currently, with a lot of papers coming out on a daily basis, and but the main sort of like trend nowadays in RLHF is actually taking the RL out of the RLHF, mostly basically doing preference training as opposed to like proper reinforcement learning. And that was really kickstarted by this, direct preference optimization method. But here, instead of basically taking the RL out of it, we revisit how we actually do reinforcement learning. At a high level, again, reinforcement learning from human feedback is the problem setup where you want to align your language model to human preferences. And the canonical algorithm that was used for this purpose was PPO, Proximal Policy Optimization, which was first proposed by OpenAI in the seminal paper of RLHF. But here we basically ask the question: is PPO's reputation and popularity merited as the RL tool for doing RLHF? So here's some background. For RLHF, it's typically done in 3 stages. The first stage is just normal supervised fine tuning, which is instruction tuning, teaching it to follow instructions. And then typically, you use the supervised fine tune model to train a reward model. And the idea behind training the reward model is you have some sort of scalar that you can optimize with RL. And typically, this reward model is initialized from the same SFT checkpoint as produced in step 1, and you train it as a binary classifier with a super standard negative log sigmoid loss on binary preferences. This is not the only way to train reward models. This is just the way that's mostly used in the literature, and yeah. And as the last step, which is actually the RL step, you maximize this reward model's reward subject to your current distribution, but you also have a KL penalty, which is actually super critical in RLHF because there's a lot of work that basically shows if you remove this KL penalty, you end up with degenerate generations. Basically, you do reward hacking, and yeah, so this KL control is super important in RLHF as a paradigm, and we'll come back to it later in the work. But yeah, so like if you're with this, 2-term objective, you basically want to maximize the shape reward, as I typically refer to it, where your actual reward signal is just penalized by a sample estimate or a fixed point estimate of the KL penalty, as you see on the bottom right. Yeah, so to maximize this objective, typically, as I mentioned before, through RL, people use PPO, and it's directly taken from the deep RL literature where it was first proposed. And its main purpose was to stabilize training and combat high variance, because those are really like the backbreaking issues in deep RL, deep reinforcement learning environments. And as an active critic algorithm, it requires training an additional network and maintaining it in memory. It also has a super complicated loss, as you see on the bottom left, which again is designed to combat quote unquote catastrophic gradient updates. as seen in the deep RL literature. It's also pretty difficult to tune because there's a lot of hyperparameters and a lot of moving pieces once you actually dive deep into PPO's implementation. But the point is, the point of this paper actually is that PPO is unnecessarily complicated, and you can actually get away with a lot less, so to say, in terms of complexity, but achieve the same performance and still do RL. Now, taking a step back, you have reinforce. Reinforce is basically the estimator that was proposed in the 1990s by Williams, so 30 years ago, and it's really the backbone of everything in RL, because in some way they're linked back to this estimator. It basically provides you with an update rule such that you can maximize a reward given a distribution. Again, it looks pretty simple, and it is pretty simple at a high level, but it's PPO also uses it at a token level under the hood. Typically, this vanilla reinforced estimator where you just weigh your gradient by the reward as super high variance. And to reduce this variance, people have devised, since a long time ago, unbiased baselines. By unbiased, I mean, if you take its expectation, it doesn't move what you're actually trying to optimize. The expectation of this term is the same as not having the baseline, but it reduces variance. And really, the role of the additional network also in PPO and general RL algorithms that are active critic or have a learned baseline is to reduce this variance. You also have, but you don't necessarily need a parameterized baseline as done in PPO and traditional RL. You can also have something like a moving average baseline, where you just take the moving average of all rewards throughout training, and that's your baseline. It's not a super strong baseline, as it's not super accurate on a per generation basis, but it does the job, as we'll also show in the paper. It's not bad, so to say. But we can do better in terms of in terms of coming up with a baseline that's really that's unbiased, but also is parameter free and is really accurate and strong. And that's really the idea of reinforced leave one out, or RLU. It uses additional samples that you generate given the same conditioning to create a baseline, and that's pretty much it. So you don't need to train an additional network or you do anything extra. You just need to generate additional samples, and then you can follow the update rule here, and you get a baseline for free. The only cost here is extra inference budget that you'd have to spend to generate K's greater than 1 completions. But in most cases, this would be preferred to having to maintain an additional entire network in your memory. Cool. So I'll take a moment and pause here if there are any questions before we sort of go into this next bit of how you actually go from PPO to the reinforced estimator. So yeah, are there any questions? If not, I can just continue to move on. Cool. Okay. So, by the way, feel free to put your questions in the chat or anything if they come up while I'm also going through this. So, again, PPO is too complicated. Reinforce is really its backbone. The argument here is you don't need PPO. Reinforce at a vanilla level is good enough for RLHF. One of the main design decisions, and the main design decision behind active critic algorithms like PPO is a problem of trading off bias and variance in reinforcement learning. And this bias and variance I'm referring to is bias and variance where you're trying to estimate a trajectory return. So you take a bunch of actions, you have a full-fledged trajectory, and then you want to estimate the total return that you got with that trajectory, and you have some samples. If you just do the traditional Monte Carlo approach of just taking a sample trajectory, adding up all the rewards along its path, and that will be your estimate of the total return. That's fine, but historically this has super high variance, and that high variance is problematic because it impedes learning, or has been shown to impede learning in other environments. So what people, that's the idea behind actor critic, is you use bootstrapping. You bootstrap off the additional network that you train, your value function, in estimating the total return. So you reduce the variance of this let's say sequence level return estimator, but then it's biased in that you're not optimizing really the same thing. It's a bit different. So this bias and variance trade-off is also abundant in just general statistical learning. So it's not anything new, but yeah, it's deeply like involved with active critic algorithms in RL. But yeah, so in PPO, you sort of have this, you do have a knob to basically tune the bias and variance trade-off. And that's through the generalized advantage estimation that's built in or typically coupled with PPO. And it's basically this, in terms of like looking at the loss function itself, the advantage A. Yeah, go ahead. Someone raise their hand. Nope. Okay. Yeah. So in terms of the loss function itself, you just have this knob lambda that as you increase lambda, you increase variance, but then you reduce bias. And lambda is itself parameterized to be between 0 and 1. And in practice, usually the typical default value for PPO is 0.95. If you turn it up all the way to 1, which is you see on the bottom right, you basically get something like, and it's really an unbiased like Monte Carlo estimate with the value function acting as a baseline, as opposed to for bootstrapping. And if you turn it all the way down to 0, you have basically the TD return, which has really low variance but is extremely biased. So you make full use of the bootstrapping in a way. Yeah. So like one of the first experiments I guess we did for in this whole line was just vary lambda, like keep everything constant in the PPO setup and just vary lambda to see how bias and variance, how trading off bias and variance actually affects your learning. And it turns out that the smaller your lambda, the worse your optimization is. On the y-axis is the actual reward, and then on the x-axis is the number of steps. So it's pretty clear signal that you don't want to introduce bias to reduce variance. Like introducing bias, or you need to forego introducing bias basically in RLHF. And if you recall, reinforce is typically, when people say reinforce or vanilla policy gradient, it's unbiased, and we'll show that style of optimization is just better than PPO because it's unbiased. Let's see. Yeah. So that's point number 1. Point number 2 is, again, you have the loss function in the bottom left. It has this clipping component, and it's designed to clip the gradients if they get too large, basically. And large gradients would cause instability. And this, again, is an issue in deep RL, and it basically kills the gradients. Even though the loss is clipped, it just kills the gradients. The reason behind this is, the function f that on the bottom left that I just didn't, like the importance sampling ratio on the bottom left. This term has really high variance. And in deep RL, that's problematic. But in RLHF, you don't really see large ratios like that in the loss function at a token level even. And as a result, if you actually track how many percentages of the time this clipping gets activated, it's something like 3%, 1 to 3%. It's super minimal. And even if you turn off the clipping, as you see on the bottom left, but it doesn't hurt. If anything, you can argue that it improves it, but there's some noise and whatnot. So yeah, the point again is you don't need to deal with high variance or high variance gradient updates in RLHF. And the last point is with regards to how the problem is actually modeled. So typically for RLHF, in RL you have states and you also have actions. In RLHF, each token is typically treated as an action, and then the partial sequences are states. Your initial state is determined by the prompt. And in practice, you actually don't get any reward for any of the intermediary completions. The intermediary tokens before the EOS token. The only token that actually gets a true reward from your reward model is the EOS token. And all the other tokens up to that point, they just carry a KL penalty. And this is really like, this observation is sort of like makes you ask, it doesn't really make sense to have tokens and actions as opposed to sequences. The entire sequence is an action if because the transitions are deterministic. You're guaranteed to get an EOS token. You can make the argument, and that's the argument we make, is the entire sequence is an action as opposed to a single token being an action. And that simplifies a lot of things in terms of both implementation and it's a nice simplification that from our results doesn't lead to a performance degradation. Yeah. So, I sort of talked about like three different things from PPO. Or three different pain points from in PPO. The first one was bias and variance, trading off bias and variance. The second one was clipping. The third one was also modeling sequences as actions as opposed to tokens. But these are all really simplifications, and the question is, why can we make those changes to the traditionally designed? The design of PPO, which was for deep RL. And the answer is that in RLHF, when you're doing it on language models, LLMs, your initial policy, your starting point is too strong. Because you do pre-training on it, and the strength of the initial policy is basically there's nothing like it in deep RL. You never have such a strong init, so to say, for RL, and this actually makes a lot of difference because, for example, you see in the plots on the bottom left, what I'm just plotting there is the entropy at every single generation step. So if you're generating 120 tokens at every single step, you look at the logits and then you calculate the entropy and then you divide it by the maximum entropy under that vocab size. So it's normalized. It's between 0 and 1, and it's really small. And especially after you generate the first token, you see a tank or a huge drop in the entropy. And that just points to the effect of strong conditioning that you get with a pre-trained language model and a prompt. So there's really two things. Also on the right, you see that basically all the probability mass at every single generation step is contained within the top 32 most probable tokens. But in theory, again, you have a huge action space, right? Because was it for llama, the vocab size is like 56 something, if I recall correct, 56,000 something. So, but in practice, because this probability distribution is super skewed, you don't have that many actions really that are probable. And like 32 or 64 actions is actually, it's a super small action space in practice. But yeah, really, the point of all of this is to say, RLHF of LLMs is really a different setting than deep RL, and a lot of the insights and challenges and whatnot do not translate between deep RL to RLHF of language models. So RL needs to be carefully thought through before getting applied to LLMs, as opposed to just taking something from deep RL and slapping it on LLMs. That's not going to work optimally. Cool. yeah, so I'll pause again here. Wait, let me try and see if I can see if there are any questions in the chat. Oh yeah, there's a question from Sergey. I am wondering why OpenAI used PPO for all their experiments and not reinforce. If it's a fair assumption that it was probably because PPO converged faster. Well, I mean, there's a couple of reasons. Well, PPO was initially proposed by both within OpenAI, and it was first applied to RLHF in the context of language models. But the matter of convergence is actually, like I'll show in the results, it reinforce a vanilla policy gradient, basically something that's not PPO. You can show it converges faster. So in the RLHF of LLMs, there could be multiple reasons why, in all the papers that came after what the first paper in summarized human feedback that's use PPO, they still keep using PPO. Like PPO was proposed by OpenAI, yada yada yada. But yeah, I mean the thing with PPO is it does require a lot of niche expertise. So if you tune it super well, it's not that it will perform super badly, but it's just the lift to get to that point is actually really considerable for your typical practitioner, so to say. Yeah. Let me reshare my screen. Cool. Yeah. So in terms of our evaluation setup, uh, there's a couple of things. So typically, people, as you know, they measure win rates. Basically, get an outside LLM or humans to compare responses generated by your model with some gold responses or another model's responses. But we care about reward optimization in RL. So we have an objective as I talked about before, and you want to maximize that objective subject to a constraint. So how you would compare optimizers or optimization algorithms is by measuring that objective on a held out test set, as we do here, and plotting it over time and see which one achieves a higher reward on based on that objective. And yet, I mean, the test bed for our setup is we have two base models. One is Llama, like Llama 7B, and the other one is Pythia 6.9B. So two base models, two data sets. One is the summarization data set from OpenAI, so the Reddit TLDR summarized. The other one is the Anthropic helpful and harmless data set, which are both like pretty well experimented with in the literature and for RLHF and prep training. And yeah, here are the results. So in the bottom right, I mean, you again, in the y-axis is just the reward, and then the x-axis is the steps. The general trend, regardless of the choice of base model and data set, is that PPO lags behind vanilla policy gradient. Vanilla policy gradient is basically if you turn, the tuning knob of PPO, which is lambda. If you set lambda to 1, make it unbiased. You also remove clipping. It reduces to vanilla policy gradient, which is just reinforced with a learned baseline. And in all three settings, vanilla policy gradient outperforms PPO. That's thing number one. Observation number one. Observation number two is that RLU, so reinforced leave one out, and reinforced with baseline. This baseline is the moving average baseline that I talked about. It still does not have any learned parameters. They outperform the token level models for most cases. Sorry, the token level algorithms. So PPO and vanilla policy gradient. And this is sort of testament or supporting evidence that if you don't need to model every single token as an action, but if you model the entire sequence as an action, you're still good. It doesn't come at a cost of performance drop, even though it makes things a lot more simpler. Yeah, and you have RLU and RAFT. RAFT is I don't think I actually touched on it, but RAFT is reward aware fine tuning. Basically, the idea is you sample multiple times, k times, use a reward model to rank those samples, and then you take the best one and do cross entropy on it. So it's sort of it's basically iterative fine tuning or iterative best of n. And yeah, so the consensus, I mean, the high, again, at a high level, sequence level methods are better, seem to be outperform token level, and also again, unbiased optimization outperforms biased optimization that theoretically has lower variance. Oh yeah, here's the thing about RAFT. So both RLU and RAFT, to be able to actually use them, you need to generate more than one sample. So if you think about a sample budget or inference budget, the argument here is that RLU is more sample efficient than RAFT, because RAFT, like I said, you take the k samples, you rank them using a reward model, and you take the best one. You discard the rest. So it is generally just inefficient. But with RLU, you can make use of the full set of samples, the full k samples that you have. And that's what actually gives it the edge over RAFT, as you can see also again in these plots, is as you vary the number of samples, k is equal to 2 or k is equal to 4, generated for each prompt. For the same number of samples, RLU is better than RAFT. And even sometimes, for example, for anthropic HH, on a Pythia-based model, it's k is equal to 2 RLU is better than RAFT with k is equal to 4. Again, talking about sample efficiency. Just so it's easier to, basically parse the previous picture in the context of sample efficiency, or if you have a fixed inference budget, if you think of it. On the x-axis here, we plot the total number of online samples generated, normalized by batch, of course. But basically, this is just the number of steps in the previous plot times k, just so we're comparing it. We just look at the budget as a means of comparison. And the y-axis is again the reward on held out test prompts. And again, unanimously across the 3 settings, so 2 different base models and 2 different data sets, RLU achieves a higher reward given a fixed sample budget in compared to RAFT, or fixed online sample budget compared to RAFT. We also measured win rates because the thing you care about is how well your final responses are aligned with human preference. And typically, instead of actually getting human annotators because it's costly and generally a super big hassle, you use GPT-4. Here, we also use GPT-4 to measure win rates against the gold responses in the SFT sets of both data sets. And generally, the trend is for the same k value, RLU outperforms RAFT, and generally vanilla policy gradient, which is again unbiased form of PPO without clipping and stuff, outperforms PPO. And reinforced with baseline, although pretty simple at a high level, also does pretty well in the category of k is equal to 1, basically where you don't generate extra samples as a means to improve or learning. Yeah. We also compare with DPO. DPO is pretty decent, but proper, mostly RLU and RAFT in most cases actually beat DPO, which is sort of testament to the online nature of the algorithms being valuable in the context of preference training. But that's just a side thing. Yeah, we also looked at robustness. So by robustness here, I mean, there's a couple of things for robustness. So by robustness here, we mean with regards to the KL penalty, or I mean, the first criteria. In the bottom right, the plot, what it's basically showing is, or what we want to compare is subject to different degrees of penalization, KL penalization. How well do different algorithms, in this case RLU and RAFT, optimize the reward, the overall reward? And overall, RLU seems to be not only be better at optimizing the reward function, but it's also more KL efficient in that if you have a fixed KL budget and you say, okay, I can only use up 20 KL, RLU makes better use of that budget as opposed to RAF, and based on this plot. Yeah, so that's one of the things we studied in the context of robustness. Another thing we also looked at was robustness to noise. So there's different ways you can study this. Let's say artificial noise injection into the reward. But what we basically did was take the reward from the reward model and add noise sample from a normal Gaussian to it, rerun the training, and measure how much was the drop in the new run compared to the run without injecting any noise. And here we just plot the difference between the noisy versus non-noisy optimization training curves. And again, overall, RLU is more robust to noise injection. And the reason for that is, well, RAFT, as again, it ranks the K samples. So it's really a discrete ranking. If you have enough noise, it perturbs that ranking such that the sample you end up choosing is not the true best sample because of the noise injection. But in the other hand, RLU doesn't make the hard decision or draw the hard boundary of like, this is the best one, this is the second best. It treats each sample individually and creates a baseline that's unique to that sample. And that's why it's more robust. It just, as you increase noise, RAFT will tend to pick more incorrect examples more often than not, and that has a big effect. And yeah, as you see on the bottom left, given the same, well, if you compare RLU and RAFT, given the same standard deviation for the noise distribution, you see that RLU has a much less significant drop in reward compared to RAFT. And oh yeah, that was actually all I had for today. In conclusion, really, reinforcement learning from human feedback in the context of language models is not the same as doing RL in deep reinforcement learning, traditional deep RL. The settings are a lot more different, are a lot different, and you need to make different design decisions for the optimization algorithms in each context. So that's point number one. And also, instead of taking the reinforcement learning or the RL out of RLHF, like what most of the techniques nowadays do, if you carefully adapt RL to the problem setting of RLHF, you consider that you have a pre-trained model, you don't have an issue with variance, you don't need to introduce bias, sequence level modeling versus token level modeling, things like that. The better you craft the better you tailor your RL algorithm to RLHF, you can outcompete methods like DPO that don't use RL. So yeah, that was all I had for today. And if there's any questions, I'll be happy to take them.